going to show you at the Institute we work a lot on characterization, mechanical characterization of real components, and sometimes they have a very complex architecture, in many cases layer architecture, again combining polymers, metals and ceramics. And today I wanted to share with you first of all some mechanical testing that we use, how we do it, how we take into account metallizations, environmental effects on the mechanical characterization of our multilayer components. And then at the end I will show you one example of a real complex architecture, how we understand the fracture, or we think that we can understand the fracture. Maybe just for you, you're not familiar, some of you, with ceramics, just to draw your attention that you can find thousands, hundreds of components in a printed circuit board mounted on top for a certain functionality to tailor the electricity flow and so on in your board. And but not only as component, you can have the substrate. In this case, it's made of ceramic, and you have here a layer architecture, a lot of layers of ceramic combined with glass, and then some metallization. So it is interesting to, first of all, you want to understand reliability of the systems, to have some methods for mechanical characterization. That I would like to show you today how we do it, how we measure the strength of real components. So we'll be looking at some variable statistics, and I will show you some local strength measurements and effects of other things. And then we will go to some real systems which can be much more complex and to see how we deal with this problem. So first of all, we want to test real components. In many cases, they have like a plate-like or disc-shaped-like structure. So we cannot really go and say make bars and make three-point bending or something. We have to adapt to the geometry. And for that, we developed what is called a biaxial bending test, where we put the plate-like components between four balls in a compression test configuration. And in that case, if we press the four balls together, we will induce in a certain small region very high stresses, and eventually you will break your specimen or your component. And you can compute a little bit and find out what is the maximum stress, and then you make some variable plots and so on. It has many advantages that we can make some local strength measurements. If we want to put in certain locations, it's very accurate, and you can put the whole thing in different environments and see some environmental assisted cracking effects, for instance. You can see also type of geometries you can test. For example, just to show an example, these are silicon chips, so brittle materials, 100 micrometers thick, and in some cases you see the dimension 2 millimeters. So you can adapt this testing and in this case localize your stress in certain locations. And this is one example. If you have a printed circuit boards, they produce millions of plates with different modules inside. We can cut off some plates and put the balls in a certain location, and then we can identify, okay, what is the strength of this particular location. And then we can do some photography and identify the failure, which in many cases occurs on the surface. These cases. Here's the example where how small differences in the multilayer architecture, how inside the metal electrodes are distributed. You can have some residual stresses, very complex. Or you have some vias or other locations. You can have, if you plot the results, let's say, in a variable plot, testing different locations, you can have some differences, which can be important for the lifetime of these components. And you see, at the end, you have thousands of components made of the same kind, with the same geometry, and some of them fail at this location, some others here. So that helps to make some good predictions. And I don't know if you're very much familiar with environmental effect on glasses or brittle materials, but it's really prominent. It's very well known in glasses, but we have it also in many ceramics, sometimes because they contain glass faces and so on. So just to show one example, if you test your components, ceramic components, in a very humid environment, you will obtain much lower strengths than if you do it in a, let's say, low relative humidity environment. And again, this is some effect that you would like to take into account if you make some lifetime predictions. This is what we call subcritical crack growth, which is similar to this stress corrosion cracking in metals. Now, to show you that this can be very important, what we do is we test the components in one certain environment, water, at different high rates, at different stress rates. So some of the testing specimens, they break within 4 hours, and some others they break within 4 seconds. So the higher is the speed, the less time you have for this corrosion, and you will get higher values. And if you go to drier environments like inner atmosphere or something, you can see how the same component tested in the same, let's say, loading conditions in one or another environment can have dramatic differences in the strength. So this is something we have to deal with when we work with brittle-like materials like glasses and ceramics, and it makes things not easy. That's why we need very nice layer structures to avoid this crack propagation, which is one thing. But it is interesting that it is not only the environment which affects this. You can have a combination, environment, metallizations, internal structure, etc. So I will not go into detail. You can find some more details here, or we can discuss later. But in some cases we do, let's say, we create some very simple structures in order to learn what is the effect of metallization, what is the effect of other things. And this is one example where, well, we just have some vias or metallization on the top, and we could see very dramatic differences. Now we have the testing method, we are aware of different effects, and now we get to the real samples. Real components are much more difficult in their structure than just one single ceramic with the top layer of metals. This is one example where you have zinc oxide as a substrate material, and you can see here metallizations inside, vias connecting, going through the material, then top metallizations, glasses to isolate, and everything. And the process of fabrication is really complex. You can have, first of all, a substrate with the vias, then you put some metallization, glass layer, another metallization, some galvanization, where you will allow other components to be placed on top and solder. So it's really complex, and I think working with layer structure, you can understand how complex can be the residual stress in this system, right? So I will not talk about residual stress here, but I assume that we have a complex residual stress. What was interesting here, and I want to share with you, is to draw your attention that some small differences in the geometry can play a huge role in the strength or mechanical behavior. These components have two sides, the top side and the bottom side. And if you look at these, they're very much identical, but they have differences. In one case, you have some metallization, and then you put some glass on it, and that's it. And the other one, let me show you here, you have some metallization, the blue is the glass, and you can see the difference here, just a small tiny difference where the metallization second one is going farther from the metallization one, and vice versa. So we were having some preliminary testing of these, and by Axel bending, and we observed some dramatic differences between top and bottom. So we said, well, let's try to make it like easier with some kind of standard bending and understand better. And this is what we did. Configuration 1 looks like this, the second one like this. We did mechanical testing. And when you look at the results, it was interesting to see that one of the configurations, despite you have an amount of layers on top, residual stresses whatsoever, the strength distribution is identical to the part material. So from the designer point of view, it's like not a bad news to say that you get a functional component and it has the same properties of the part material. The problem was with the configuration number 2, You look at the numbers here. The reason is why. So we wanted to understand, and we did some failure analysis. This was the first thing we do. We made some cross-sectioning, like that, on broken specimens. And you could see both specimens were having the top side under tension, so you have to look at this particular location here. And you could see that in one case, the crack starting somewhere at the surface was going and eventually penetrating the metallization here. Whereas in this configuration, the crack was starting there and just going through the layer. At this particular location, there was no metallization here. So based upon these, we were thinking that maybe that was this metallization. First of all, we identified a critical location where the highest stress concentrations could be. And this was qualitatively predicted by a model. But based on thinking about this layer structure, we were thinking that maybe cracks could be somehow arrested at this tough metal layer and prevent the failure. Whereas in the other case, there is no layer to prevent the crack from its propagation. Now, there was just a model back. What we did is that, I think it's interesting, some preloading on rigid samples where we just do not break the samples, we just preload them and then examine how is the damage on it. So I think this focus IMB technique is very useful for these brittle materials where you can induce some damage and then look at the location that you have preloaded. With this, we did 3-point bending, and then we went to the SEM, make some focus IMB, and then if you look inside, you can identify here this nickel is the yellow layer, then you have metallization, glass, and so on. And if you look closer, we could see for this particular configuration how a crack originating due to residual stresses of the system could propagate, but it will stop in the metallization underneath. Whereas for the other configuration will cause catastrophic failure. And with that was what could explain the results that otherwise could be very difficult to understand if you don't have this strap-on, let's say, approach. So to summarize this talk, I think this is part of the conclusion from the previous talk, that the functional properties, if you want to have functional components, you need to have a certain structural integrity. This is very, very clear. And to understand and make some reliability models, you need to have some testing methods which adapt, in some cases, to the real components. With this method, and I'm doing a little bit of marketing here, because it can be very practical for some things, we can do some local strength characterization. We can see effects of environment that with other testing methods could be very difficult to discern between small differences, let's say. It is interesting that you can check what is the effect of different patterns, different metalizations, combined effects of structure, architecture, and environment. And for the example of real components, we could also see that the geometry, just a simple difference in geometry, could have dramatic meaning for the lifetime. So I would like to thank many different colleagues working and the financial support by the Material Center, the Open and Comet program in Austria. And thank you very much for your attention.